Okay, so hello everyone. Thanks very much for stepping by. Welcome to this first arXiv paper pitch. It's about almost relevant corrections for direct measurements of electrons G factor, and it's work done in collaboration with Felipe Asenko and Sergio Hochmann, present here, and my name is Benjamin Koch. So an outline of this short summary is that first I want to give a short introduction about G-2, and in particular about the direct measurement of the factor G-2 as it's done today. Then I will turn to a description with an effective field theory approach, and then how this can be used to find corrections arising from strong background fields, in particular strong background magnetic fields. In the end, get to some conclusion. So let's start with the introduction. G-2 is a very successful story of two players, theory on the one side and experiment on the other side. And what is the G factor? Well, it's a coupling, a parameter, which describes how strong is the coupling between spin and external electric and magnetic fields. So one can start this story, it was known before, but here we can start the story with Paul Dirac in 1928, when he came up with this famous Dirac equation. And within this equation, the G factor is actually determined to a fixed value. It's exactly 2. So 20 years later, by Polycarp Kusch, or almost 20 years later, he found that G equals 2 is a very good approximation, but it's actually not the true value. The experimentally true value seemed to be different from 1. So this, of course, on the other hand, triggered again theorists to think about it. And many contributed to this. Let me name here Julian Schwinger in the year after that, who came up with a quantum field theoretical explanation that G is almost 2, but modified by a factor of alpha over pi. And this is in a one-loop approximation. And from here, the story started, continued, and there are many, many contributions on both sides, on theory and experiment, which I have no time to mention now. But let me just mention that the most recent experiments of the direct measurement using penning traps, which is indicated on the one side, and the theoretical contributions are summarized in this long formula below, which make a relation between the G factor and the electromagnetic coupling and other parameters, alpha and other parameters of the standard model. So let's look a little bit at this formula. What is nice and amazing about this formula, that it relates to independently measurable fundamental quantities. So G and alpha, you can measure them in different experiments. So one can check this prediction of the standard model and of QED in particular by making those two measurements. So here's an example of these measurements plotted against time. So in 2008, there's the latest direct measurement of the A factor, which we call AD for direct. And one can compare this to the other A factor you calculate from measuring alpha. Yeah. So this is the red and orange plot, or yellowish plot, which are given by these publications. And one sees that until 2018, there was a slight tension between direct and indirect measurement. And from 2020 on, there was a new indirect measurement, which gave a different tension in the other direction. And the tension is actually smaller and not so significant. So now our idea is to address this from looking at the direct measurement side. Okay, so here comes the penning trap experiment. It's basically a magnetic field, and you have to confine the electron. You have different eigen frequencies of this system. It's pretty complicated. So let's look at a simplification. So in any case, the eigen frequencies of classical systems in quantum mechanics correspond to the eigen energies of the system. So let's look at the eigenenergies of an electron confined in a magnetic field first, and then look for further corrections. So here's the master formula of the eigenenergies used by the experimental colleagues. And we have the quantum numbers n, corresponding to the n quantum states, and plus minus En corresponding to the spin orientation. And on the right-hand side of this energy formula, you see two important quantities, which is one is delta C. So delta C is the dimensionless cyclotron frequency normalized by the mass of the electron, and A is the G factor. And now we see in this formula A appears. So if we measure the right energies and make the right mathematical operations with this, we can solve this equation for A. And this is done by what we call the master equation here. So you rest E naught plus minus E1 minus and divide this by what is given in this formula. According to this formula, the result is A. And since this is known as the direct measurement, we will call it AD, as opposed to the indirect measurement where you just measure alpha. So you measure these energy transitions in the cyclotron system of an electron in a magnetic field, and the result should be AD. And this result was measured to this impressive precision given by the number below. Okay, so where does this formula come from? If you want to know corrections, we need to understand where does this formula come from. For me, the best way to understand this is within a description in effective field theory. So we can write down the Lagrangian of the Dirac equation, which is the first two terms here, and then add an effective coupling we call A, which is just the moment we are interested in, the anomalous magnetic coupling between F and the electron field psi. For this effective Lagrangian, now we can derive the equations of motion given here, and then one can proceed to solve the equations of motion for the simple system of a constant magnetic field. And one has to choose a gauge here, but okay, here comes the solution. And the solution has, of course, eigen frequencies, so the eigen energies, which is given by this formula here with the square root inside and so on. And already you see A appears in this formula. Okay, now the last step consists of expanding the solution for small cyclotron frequencies over the mass, so small delta C in a power series, and you get exactly the formula we have been looking at before. And now we expanded it to one more order just to see that this can be continued if you have a higher precision if you want so. So this procedure contains expansion. So what kind of expansion does it contain? First of all, it contains an expansion parameter when you write down the effective action. And second, it contains an expansion parameter when you assume small cyclotron frequencies. So we have on the one hand side in the effective action a loop expansion. So the expansion parameter is the fine structure constant 007, more or less. We call this epsilon. And then you have a magnetic field expansion, which for the given experiment, of course, depends on the experiment, is 10 to the minus 9, so epsilon to the 4th. Okay, and with this, the energy formula we have been looking at can be written as a logical power series in epsilon or alpha delta C, which is given here. So you have order 1, order delta C, alpha delta C, delta C squared, and so on. Oh, what does so on mean? So this was the question we tried to answer with Sergio and Felipe. So what's next? What is the next term here, given the amazing experimental precision? Well, if we want to discuss what's next, we have to realize that there are further small parameters coming into the game. So loop expansion, we know this. Magnetic field expansion, we know this. So you can have also a parity violation contribution coming from weak interaction processes. So here the parameter can be the mass of the electron over the mass of the W or mass of the set. And you have further electric field expansion. So the experiment contains, of course, an electric field. And this is much weaker, but still here we have a very small expansion parameter, epsilon to the 6 actually. So those are the 4 expansion parameters we have to consider. And now let's look at the dimensionless ratio of the energies over the mass. And this normalized to the cyclotron frequency, delta C. So we divide by delta C as is written here. And we can make a very nice plot. So let's look at this log scale plot here, where we have the precision of this energy. And here we can just show what is the experimental precision. It goes down almost down to 13 orders of magnitude, 10 to the minus 13. Then we can look at the formulas which are used for the calculation of the A factor in those papers. And this is the theoretical expansions by the experimentalists. And this goes down to 10 to the minus 9. This is, so the game. And now the question is, given that the green zone is like slightly larger than the red zone, is there a crucial parameter or a scale present in this non-overlap region? Okay, so whereas, for example, the mass, well, the mass is huge, of course, it's here at 10 to the 9. We have normalized it to the cyclotron frequency, so this is 10 to the 0 or 1. Then we have the actual observable G minus 2. This is of the order alpha over 2 pi. Then we have the relativistic corrections, and those are the ones which we had in this master formula in the denominator. And then we realize, interestingly, then you can have strong field corrections in the presence of a loop. So it's a loop, so it's alpha, and it's strong field, so it's delta C. And even more, you can have parity violating contributions, which are alpha delta W squared. You get this from calculating this Feynman diagram, for example. Then you have delta Z, which is very tiny, as I mentioned before, and further relativistic corrections or loops of further relativistic corrections. So this is the scheme. And now, of course, we see that there are two relevant scales which might be important for this experiment, given the large precision of this experiment. So now let's look how important they really are. And we do this by using an effective field theory approach. So we take the Lagrangian we have been looking before, and now we add additional operators or couplings, which we take 4 times 4 matrices. They have to be bilinear, Lorentz covariant. They have to be gauge invariant and up to 3rd order in the external electromagnetic field, in our case, only a magnetic field. And we also consider parity violating operators, so might be an F mu tilde also around here. So in schematic, we have this type of Lorentz bilinear covariant contributions, and we can write down those Lagrangian contributions here. So delta L is the new Lagrangian contribution, and there's a whole class for each Lorentz type, and each one comes with a parameter of the effective field theory, which we call xi something. Yeah, so we have many xi's here, and for those couplings, we can for each one calculate what is the contribution to the actually energy state, En plus minus, and this contribution we call delta En. And this is calculated using the eigenfunctions we have found before, and then just doing perturbation theory to 1st order to see how large is this contribution. So you find something for most of those operators, you find something, and this is what's shown here. Of course, it's not really instructive to stare at those results. So we summarize this here. So here's the sum of all those corrections. So what we see here is delta En plus minus. So the corrections to the energy formula, to the standard energy formula, considering all those couplings. Yeah? And most interestingly, here in the first line, we see actually the type of corrections we have been looking for, yeah, and also the order of magnitude we have been looking for, because the first term is alpha delta C to the 1. So this guy can actually be really important, like we expected. Okay, now what we have to do is use again this master formula. And since we are looking at corrections, we have to also improve this master formula in the numerator, going to 1 more order in delta C here, but this can be done easily. And now the energies are corrected. So the master formula is corrected, and now AD will give you a different value as compared to before. So this is what, when you insert our corrected energies into this master formula, and you see now that there's a difference between AD, so the direct measurement using this formula, and AA, which is the parameter actually appearing in the effective Lagrangian of the theory. And they differ by all those terms following up here, and we make the expansion in epsilon to the 11th order, let's say here on this plot. So this is the important message here. The direct measurement is not the actual parameter in the effective Lagrangian, so one has to correct for this. And now, in order to understand these corrections, let's study two benchmarks. First of all, the parity even benchmark. So in this case, we set all parity violating to 0 and set all the parity even stuff to 1 or 1/2. And for QED, let me mention that if it would be pure QED, the size would be of order 1. Okay, so here we see that the energies get an important correction, which is only of order alpha delta C. So this would be measurable, but important. But as we can see in this contribution to the energies, the quantum numbers n and the quantum numbers plus minus do not appear. And this has the bad effect. If you look at energy differences, this stuff cancels out. So you don't actually see it in the AD, in the master equation. And this can be shown by this plot. We show again here the difference between AD and AA, which corresponds to the difference between direct measurement and indirect measurement. So as red zone, we have the indirect model. As orange zone, we have the other indirect model. And the blue zone is given by the direct measurement. So, and what is in black here is a function of our parameter xi, so the correction of the direct. So this depends, of course, how much the parameter xi, what's the value here? And we see if this parameter has the order of magnitude of 10 to the 6, one can address the discrepancy between direct and indirect measurements. Okay, nice and fair enough. But as I mentioned before, we expect this to be of order 1 from QED. So no way that we can see it given the actual experimental precision if it's only QED. Similarly, for the parity odd benchmark, so we set all parity even to 0 and maintain the parity odd operators, and also expect that this parameter is of order 1. And again, we find the corrections to the energy states, and this one has now a plus minus here, so it's a good sign. So it will appear in the final formula between AD and AA. So we have a correction here, and this is shown by this figure. And we see again, if the value of this parameter xi is of the order of 3000, we can address, or minus 3000, one can discuss this discrepancy between direct and indirect measurement in the light of those new operators. Well, 3000 is small, but it's not of order 1. So this is explaining somehow the title of the paper, yeah, almost relevant contributions, because it's not really measurable given the experimental precision. And this is also the end, basically, of this short summary of this paper pitch. So let's go back to the conclusion. And so this conclusion is best made by looking at this energy scale plot. So we expect from orders of magnitude estimate to have important corrections to the energies. One would be alpha delta C, so from a one loop contribution, and the other would be alpha delta W from a weak one loop contribution in a strong magnetic field background. So first of all, the weak contribution, the parity violating contribution, cancels out directly when you calculate the expectation value of the energy, because it's different types of eigenfunctions. So this one goes out, but the alpha delta C is still in the formula for the energies. But this contribution cancels out when you look at the observable alpha IAD. So there you have the resting of different energy states. So this goes away as well. And the only thing which is left over are sub-leading corrections, which are, for example, indicated by alpha delta C squared or alpha delta V delta Z over delta C. And those are given the actual experimental precision, not yet relevant. And what is the take-home message? So the take-home message is that in principle, AD is not AA. So the direct measurement is, as the given formula was taken, not the same as the actual parameter in the effective Lagrangian. And this might be and will be useful for beyond the standard model studies, which have new operators in their theories. And one can look at our table and say, oh, I have this type of operator, so this will modify my value in the direct measurement experiment. And that's basically all we wanted to transmit in this short presentation. the 20 minutes are basically over. So thank you very much for coming. And yeah, hope to see you soon.